Yeah, good evening everyone. So welcome to first workshop of the power electronics event Simulim. So today I am Lakshit Vyas from electrical part 3 and today I and Astitwa are here for taking your first workshop. So let's start. So I will be covering MATLAB and Simulink basics. So first of all, what is MATLAB? It stands for Matrix Laboratory. It was developed by MathWorks. Initially, it was used as a powerful calculator, but later it kept on updating. And apart from this, it is a metric-based programming language also. So it is similar to Python in one way that it is an interpreted programming language, which means that the commands are executed line by line. So let's say you have a script having 10 lines of code. So if there is an error in 7th line, let's say, so the commands from first to 6th line will be executed, and after that the 7th line will give the error. So this is different from other languages. So apart from simulation, there are other applications also. So you can take a look over it, like machine learning, algorithm development, and Simulink. It is a MATLAB based tool which is used for modeling, simulating and analyzing the systems. Basically we will be creating electrical circuits in this tool, and then we can also use MATLAB language for analyzing and all. So let's start with the practical. So yeah, so in this window you can see this on left hand side there is current folder named window. So you can browse here and open your required folder in which you are working. Then we have command window here. You can type the codes and all here and get the output here itself. So let's say I create a variable a which is having a value 4. So you can see on right hand side there is workspace. Here the variable is stored. You can also double click on it and there is a window opened to show all the like stored values and all. If there is an array, then you can see it that also. Now to clear this, you can use clear command to clear the workspace, and to clear the command window we can use CLC. And there is you can create a script in MATLAB where you can write your code all at a place and it will be executed if you run it. So there is one more type of script, live script, which I have created for tutorial. Let's open it. So in this is a more interactive type of script where you can, this is divided into pieces of codes. This yellow blue block you can see, and to run this line of code you can press Ctrl plus Enter. So I have created this for as a tutorial to get acquainted with this language, and you can use this as a, let's go through this quickly. So you can create variables without specifying the data type. Like you can just write the name of variable and store the value. And you can use this command whos a to know all about what is this variable, what data type it is storing and all. So you can take a look over it. Like this is a string. Now for naming variables, as in other programming language we have some rules. So here a little bit different, like it starts from, it should start with a letter only, then it is same that it can be followed by letter, digit or underscores, and we cannot use keywords and all the rules are same. And one thing we have in MATLAB is built-in variables which are having predefined values. So it is recommended to avoid changing the values of this variable. So I and j are used for creating complex numbers, and pi is the value of 22 by 7, as you all know. Then this answer variable, what it does is it will store the previously assigned value if it is not assigned to any variable. Like here we are assigning this value to a, so it is stored in a, but if we don't assign it to a, then it will be stored in answer. So these are the inbuilt variables. Now coming to input and output. So as in other programming language, you can also take input and output this in this language also. So this is the syntax for that, and let's run it. So here you can see that it is asking for input in the command window. And one more thing, that if you put a semicolon at the end of any line, then it will not display the output of this assigned variable. Yeah. You can also take a string as input using this syntax, and then for displaying we have two things, like first is disp and second is fprintf. Now coming to the most important part, matrices or arrays. So in MATLAB, each variable is treated as a matrix, even if it is a single digit number or anything like. So as we have seen above, this a variable, which is simply a number, this is also a 1 cross 1 matrix. Now to create a matrix, you have to just type space separated or comma separated values inside the square bracket, and here the indexing will start from 1, not from 0. And you can also use colon operator to create an array like this. This will create an array from 1 to 10 integers, and there is another version of this, like you can define a step size. Here the step size is 2, as you can see. If I run this, then it will have the values 1, 3, 5, 7, 9 with a step of 2. This step can also be a fractional number, like here we have 0.2. So there is one more inbuilt function to create an array. So it will do the same thing. It will create an array which starts from 1 to 10, 1 and ends with 10. But here we are specifying the number of elements we require in the array. So common difference or the step size we don't have to care about it. Like we are taking 10 elements, so it is simply displaying 1 to 10. If we are taking 100 elements, then this is the array. You can view this 100 elements. Now for 2D array, what you have to use a semicolon to end the column or end the row. First, like you are typing all the values of first row, then you will use the semicolon to end this row. In this way you can create a 2D array. Now there are some inbuilt functions to create arrays. You can take a look over it afterwards. This will create an identity matrix, and this will create a random array. Now for indexing of 2D array, again we can, the indexing will start from 1 only, and you have to pass the value of row and then the value of column. Like here I have passed an array, but you can simply pass numbers also. So this will return the second row and first and second column. So if you are simply putting a colon, then it will display all the rows, and this AND keyword means the last column. Now for understanding logical arrays, this means that whenever we have any two arrays, and we are performing a logical operation on it like this, a less than b, then the array which we get will be a logical array. It will be only having 0 and 1 values, for 1 for true and 0 for false. And when you pass this logical array as an index to any other array, so it will give you the corresponding values of the elements of this array which having one value in this index. Now coming to operations. So here in MATLAB we have two types of operation. First is matrix operation and other is element wise operation. So let us create two matrices. Now if we multiply these two matrices, it will be matrix multiplication, which we generally do, right? And a by b is simply a into b inverse. This is matrix operation. But if we use dot before the variable, before the operator, like a dot into b, then it will do element wise operation. So it means that this 1 will be multiplied by 5, 2 by 6, like this. Now you can also have operation between matrix and scalars. Scalar means simple number. So if you multiply a matrix by a number, it will multiply with all elements of this matrix. And if you raise the matrix to a power, so if there is a dot, then it will be element wise operation. So all elements are separately raised to the power 3. And if there is not a dot, then the matrix cube will be performed. Okay, you can also perform sign of this matrix and all other operations. You can do transpose of matrices. So we use a single quote mark for doing the transpose. And let's say if we have a matrix with some complex numbers, so this simply a single quote will do transpose as well as complex conjugates of all the elements, as you can see here. But if we use dot and dash, then it will do only transpose. Now coming to some utility commands, like you can use this for documentation and all. Now loops and conditional statements. So you might have studied this in your CSO 101 course and all. So you know what is if else loop, if else and all. If this condition is true, then it will be displayed and all. You can check this. There is the switch case where this value is displayed based on the variable which we pass to it, based on different cases. Then loop syntax is also almost similar to what you have studied. While loop will run until this condition is false. For loop, there is one difference in the syntax, that you are passing an array to this variable I. Like as we discussed above, that we can create an array from the colon operator. So an array of 5 integers, 1, 2, 3, 4, 5, will be passed to the variable I, and it will iterate over that array from starting to the end. Okay, you can take a look all this. Now coming to plot. Plot is a very the most general function used in MATLAB for plotting, and in this you have to pass two arrays, one for the x-axis values and other for the corresponding y-axis values. And you can use this command hold to plot this multiple graphs in the same window. So let's run this. You can also do formatting and all in this graphs, and that you can explore yourself. Now for functions, one important thing to note about function is that you have to always define it at the end of a script. And this is the syntax for defining a function. This is the variable which will be returned to the caller. These are the arguments, and this is the body of function. We can call this function and see the result. And there is a special character @ which will be used to create function handles. It is just another name for a function, like f1 equal to @ the function name which we defined earlier. And if we run this, we can get the same output. So using this special character, we can define the functions in one line. Use in this way. In bracket we are passing the argument, and this is the expression to be returned. So using this knowledge, we can use fplot. This is another function for plotting, and we can directly pass the expression inside it, and it will be plotted. Okay, so you can use this tutorial. We will be sharing with this with you. Now going to the another important part, that is Simulink. So you can create a blank model here. So first of all, you can go to the library browser. Here you can see it, and in this we can see there is Simscape library. Inside that, go to electrical, and then specialized power system. So this is the library which we will be using mostly. So let us start. So first of all, we have to it is compulsory to add this block power GUI. Without this, the model will not run. Then you can search for the name of block if you know the name, or here, like I am searching. So this current measurement block is used as an ammeter. Or you can directly search it from, like you can double click anywhere in the screen and you can type the name of block. So I will take all the blocks quickly. Make sure that the blocks are from specialized power system library. You have to use this scope for displaying the output or plotting the signals, and for taking RL and C passive elements, you have to use series RLC branch, this one, and you can just drag and drop the terminals to make the connections. Emitter is connected in series. Okay, you can do this. The voltmeter is connected in parallel, and the output of these are sent to the scope. So you can name these signals also by double clicking. And now let us run this. When you will double click on scope, so you can see this. So why it is appearing so congested? It is because that the frequency of our source is okay. We have not talked about the properties of blocks. Let us see that first. So when you double click on any block, you can see the properties. You can change the properties like peak amplitude, frequency and all as per your requirement. Then you have this RLC block. You can take whatever load you want. So I am taking resistance of 10 ohms. Now you can run the circuit from scope also, and you can see that it is very congested. If you will zoom it, then you will come to know. So the reason for this is that the frequency of our source is 50 Hz. So the time period is very less. So you can see we are running it for 10 seconds. So in that time, thousands of waves are generated. So we will reduce this time to 0.04. So again, if you will run, so you can, in this way you can make the circuits. Now quickly we can see how to pass this signal into MATLAB. So you can use workspace block, two workspace block. Let's say you want the current signal to be displayed in MATLAB as an array. So you will give it as an input, and you will change the variable name to I and save format to array. So now if you will run this, the variable will be created in the MATLAB workspace. So clear that. So you can see this out variable is created here. If you double click on it, you can see the I variable which we have saved. So in this way you can do that, and using a new script you can perform the analysis and all. Like you want to see the peak of this array, so you can take max of out dot the name of the variable which you have saved in the Simulink. If you will run this, you can get the output. And one more thing, that let's say you want to change the frequency of this source. Every time you can't do this like open the properties and write the frequency. So we can create a variable for that frequency. It will be appearing in the MATLAB window again, workspace. This frequency again, you can change it and do whatever analysis you want. So this is all. One more block is there, MATLAB function. So this block is used to, like if you double click on it, it will take you to MATLAB window. So you can type your code and you can do the operations which you want with the signal. You give an input and it will be performed the calculation and you will get the output. So you can explore it. Now that you have, can anyone tell me what is the resonance frequency of RLC circuit for AC input? 1 by root LC, right? Hertz. So I have already created a model of RLC circuit. With AC input. One by 2 pi root L. So I have done all the already I've created a model with variable frequency and all, and I've created a script. So what I'm doing is I will, and I also I have this current array as input in the workspace of my MATLAB. So I will do, what I will do is I have a script already. So in this script I am storing the current peak. I am simulating the MATLAB model every time. Like there is a for loop and you are simulating it for different frequencies. एक काम करो, calculate the resonance frequency for this circuit. 10 microfarad capacitor and 500 millihenry inductor. Okay, you will get it as 71, around 71 or something. So I am simulating it around 60 to 80 frequency, and we will see the effect of changing frequency in the current. I am also, at last, after simulation, I will plot the I versus omega, that graph which you have studied in resonance. So you can see the frequency is changing here from 60. After the 71 value appears, the peak will start decreasing. So in this way you can create your models, do analysis with MATLAB coding and all. So we will share all these files with you, and you can do it yourself and check all. So now this is all for MATLAB. Now Astit will be guiding you over for control waveforms and modulation.
स्ट्रीम कनेक्ट हो जाएगी ना. Yeah, hello. So now am I audible clearly? Yeah. So okay, so you just saw that how we can assemble a blocks in Simulink model and then create our various systems and simulate all their properties. So next thing is like how the blocks communicate with each other. They use some kind of signaling. So they're saying some form of signal or another. Yeah. Okay. Yeah. So they use some kind of signaling that effectively communicates this inside the system and runs it according to our desires. So the basic need of control waveforms in a system is especially for power electronics perspective, is for power quality, as you might see. So some you might say have seen that if in LC circuits, so the power factor comes into place. So that is actually the result of the offsets. That's the signs of waveforms. It's like power quality, the efficiencies of your controllers, the protection. There are various protection circuitry that works upon generation of special kind of waveforms to trigger the fault in abnormal conditions. And lastly, load regulation. So in some cases that when your load is not constant, sorry for that. So when your load is not constant, it might be variable. So you have to change your control signaling to demand that load, so that the system doesn't collapse and your supply is maintained. Now, what are the various kinds of waveforms that we use? So basically they are divided as two waveforms, unidirectional and bidirectional. And as the name suggests, unidirectional waveforms only flow in one direction, as you can see in here. So there is a square wave, it's just on the one side of axis, it doesn't never crosses the 0 point. And on the other side, the sine wave or any kind of bidirectional wave oscillates between the positive parts and the negative parts, repeatedly crossing the 0 point, right? So this is a very primary classification. Now what kind we have few characteristics of waveforms that you might be knowing from your school days. So basically the wavelength, so wavelength is your time period that we basically use, time taken to complete one cycle, right? The amplitude, so maximum displacement, we measure it in terms of voltage, volts and amps, because obviously we're electrical engineers. And there is your frequency, so number of cycles completed in 1 second. Now let's move on to the commonly used waveforms that render our devices in our day-to-day lives. So first of all, you have square waveforms, you have triangular waveforms, you have sawtooth waveforms, and you have got trickle and pulse select waveforms. So we'll be going through that quickly, so to see that what are their properties and how we can use them in our lives. So first of all is your square wave waveforms. So as you can see, the square wave forms only have two discrete levels, only a 0 and a 1. There's nothing in between, and the transition between them is called your edges. So there's your low level, the bottom one, and there's a high level, and then there's your edges, that the part of transition. Okay, the width of the positive half is also oftenly mentioned as your pulse width, and the cycle of the period is just one whole completion, one whole. And this kind of signals is widely used in microelectronic circuits as your clock signals and just timing purposes, so that suits it well. The next kind of waveforms that will be looking especially important in power electronics is your triangular waveforms. So in these kind of waveforms, you got two levels. So it got discrete levels actually, it's just not. So it goes from your 0 to peak to negative peak in steps. So each of these will be having some kind of value. So if you see, if you can count, it will be infinite many values in a continuous signal, right? So this particular part is called your positive ramp, as it has a positive slope, and this particular part is mentioned as your negative ramp, and radio peaks, amplitudes, and the rest of the definitions remain the same. And these are majorly used in your carrier frequency waves. So we'll be discussing later that how are they actually involved in. So, and obviously with the variation of these ramps, we can actually change the average value of the sine waves of the triangle waves to get the desired output. And a very special wave very famous derivation of this is a sawtooth waveform. So it's just basically either doing the falling time to 0 or rising time to 0. So basically it only has one ramp and then immediately falls it. So it also finds in similar uses, even in more uses. It's very popular in music production instruments, and because of its harmonic contents that we'll be discussing later. And it's just basic it. Yeah. So the next is your trigger or pulse waveforms. So these are specially used to these are actually used to trigger the happening of an event. When you want to do something at an instant, you just trigger a wave pulse that this is the incident I want to do something. So this is the application of your pulse waveforms basically, and you can find them in timers. When you have to find a timer, you can find them in flip-flops. A reset condition, just you have to give a pulse. If you could give a continuous conditions in your even in a clock signal, so it might race around, right? And even in power electronic devices, semiconductor switches such as thyristors, if you might be familiar or you might be studying it later in the next workshop. A pulse signal is required to start the conduction, and the thyristor stays conducting until the current through it is reverse pass. So we just give them a pulse signal and then it conducts accordingly. Yeah. Now the next topic comes of the modulation. Now this is specifically for how actually we use these waveforms. So modulation, as you have already read, is just basically the process of superimposing a modulating wave over another wave, that is we call as carrier wave. So carrier waves, as our triangle waves, have their characteristic amplitude, frequency, or this phase varied through a modulation signals that we provide, or we want to be transmitted, or the voltage. Then the basic vary. So the amplitude of modulating wave to that of a carrier wave, you might be knowing that is called a modulation index. And in specifically in power electronics, this modulation is used to actually a very important in conversion of DC to AC signals, because when you want to specify a particular signal of a level, you want to get the average value. So in the signals, you can just digital signals, this only trigger between 0 and 1. You can switch on a MOSFET, you can switch off a MOSFET. You can't just intermediate it. That the part is very low. The losses and part are very high. So to effectively produce an average voltage according to that, so we perform a certain kind of switching pattern, and that is what is modulation is. Okay, so this term is quite famous. So the pulse width modulation, you might have heard around it a few times. So basically what we do is just we vary the width of this pulse, so this positive part, to get an average value according to our need, according to our application, according to our system, right? So integrating over a few to get the average. So you can just basically f of t is your wave. You can integrate over the period, and you can find out that the average value that you can get from this is duty times the max signal. So this is our y max, and plus 1 minus duty times your y min. In typical cases, y min we keep as 0. So this is basically what duty times of the amplitude of your square wave signal, right? And by varying this duty, the d signal, you can actually change the average value of the signal. And after filtering, so hopefully if you are not familiar with the term filtering, so filtering is just removing the symmetrical components, right? So it just leaves us with a DC offset. That will be your average value of the signal. So after filtering, you get this average value. Now there are various kind of pulse width modulation systems. So they are very specific to our application efficiencies and very strong in their particular fields, and have been developed over the years. So first we have very simple, the single pulse width modulation, and these are very simple, just one pulse in one single period. Okay, so then we have multiple pulse width modulation. So there are your multiple pulses in one period. Then is just sinusoidal pulse width modulation. So this is actually when you average the simple single pulse width modulation or multiple pulse width modulation, you get a constant average signal. But when you try to filter and get average value of a sinusoidal pulse width modulation, it will give you a sine wave, right? And similarly, we have something called a space vector pulse width modulation. So this waveform is especially useful in control of motors, high motors. So you don't need to exactly know about this in detail, but having some ideas really good. Now going at a bit, how do we actually do it? So single PWM, you can see that we have various percentages of duty cycles, and according to the formula that we showed earlier, the amplitude is duty times of your amplitude. So you can actually calculate that in the 0% duty cycle, the average value of the signal is 0. In the 25% duty cycle, you may having a quarter of the amplitude, as you can see. And as the duty cycle increases, the average value of the signal also increases, as you can see here. Here it's 50%, 75%, and 100% at this the full amplitude of the wave. Okay, yeah. So now comes the question, how do we actually generate it? So we can decide that we want this duty cycle, but how do the circuits will know it that we want it? So we have some various schematics, various arrangements that can do that for us. So can anybody tell me what this device is? Not yet. Okay, you might want to rethink. It's not particularly. It has two inputs and with some labels. Okay, so no problem, no issues. So yeah, op amps are a correct answer. So op amp, and this op amps is made up of transistors, but this is a different thing. Yeah, it's a whole like whoa. So op amp is specifically configured in a mode of a comparator. So op amp amplifies the signal. Comparators is just the amplification is so high that there is only two levels. if your this specific plus point called as non-inverting input is greater than your minus called as inverting input, then it will give high output of whatever the plus is it's. And if it's low than that, if the plus input is low than your minus input, then it will be going low. So just a simple comparator. Alright. So in the inputs of these comparators, we provide two signals. So here comes our triangular carrier wave. So as I mentioned before, this is a very important waveform in power electronics. This is actually the go-to carrier wave for almost all the applications. And then on the other side, we have the control signals. So whatever signal we want to modulate, right? So in this case, you can see that we have a control wave, this triangle wave, the yellow one, and we have a control wave, this flat one, right? And we are basically comparing it. So when the control is on minus and this triangle is on plus. When the plus input is lower than your control input, so the signal is low. Yeah, sorry. And when this the plus input, the carrier wave, is higher than your control input, it's high. And it's basically repeats all over the cycles, right? So we have effectively produced an output signal that actually has our control voltage associated with it. So when you try to filter this pulse, when you will filter this pulse, so you will get the average voltage exactly equals to this control voltage, right? So this effectively have modulated our control voltage over carrier signal at a discrete level. So this control can be anything between 0 to 5, right? If you are using a 5 volt system, and we have effectively just communicated into 2 levels, so that which we can switch a MOSFET or a transistor on and off directly, right? Now this is basically how we can generate a waveform with average. Now, if we have such a good waveform, so if we can average it so well, so why do we need other forms of pulse width modulations? So there is a certain disadvantage of a square wave waveform. So that is the problem of harmonics. Anybody here knows about harmonics? Anybody here has heard about Fourier transform? Yeah. So Fourier transform is basically breaking this a periodic signal into its component sine waves. So as you can see here, we have one fundamental sine and superimposed with multiple high frequency sine waves. So these high frequency sine waves are harmonics, and most of our devices just don't like them, right? So they don't function efficiently with them. It reduces efficiency, it reduces their life expectancies and like that. So these all are associated with the square wave signals. That's why we try to minimize these this higher harmonic terms and increase the intensity of a fundamental terms that we want to use the power from. So for that purpose, we have the next modulation technique, which we call as sinusoidal pulse width modulation. So sinusoidal pulse width modulation just as same the generation for the normal pulse width modulation, and just with the difference that we use a control voltage of a sine wave instead of a constant wave. So in the in the control waveform, instead of providing a constant signal, we instead provide here a sine wave. So this sine wave is then compared. Just a second. Yeah. So this is your triangular wave on the one of your inputs, and then use your sine wave. So sine wave generator can be used from directly analog devices or something like that, and then we effectively then just compare them and generate this variable duty cycle signal. So as you can see here, this is dependent actually upon the intensity of this. So in the specific period, you can say when the sine signal, so this is your triangle wave, this is your sine wave, and the comparison is there. So in this particular time, whenever the sine wave is less than your triangular wave, it will effectively produce low, and when it is higher than your carrier wave or triangle wave, it will produce high. So it is this concept on the, and obviously, and this the crossing period overly increases with time as the sinusoidal signal proceeds towards its maxima. So the duty cycle corresponding to this maxima is higher than the low points. So in this low points, you can see that as the sine is decreasing, this the effective rate in which the sine signal is greater than your carrier signal, it's decreasing. So the pulse here get thinner and thinner. So if there is any doubt in this section, please let me know right now, because this is a bit difficult to grab at first, but I'll explain it to you. Okay, so I'll just quickly use the blackboard. Yeah, hello. Okay. See, so this is a normal voltage versus time graph, and this is, let's produce half a triangular wave. Right, this is your carrier wave, and the modulating wave we have as a sine wave here. Okay, now let's map the areas where the sine wave is greater than your triangular wave. So in this specific, so if not solvable, so you can see that the sine wave is actually greater than your triangular wave part. So you just, for this part, the duty can be set to be high. Then this part, that your triangular wave is greater than your sine wave, right? So up to this point, it's going to be low. And then again, in this part, your sine wave is greater than your triangular wave, so it will produce a high. Similarly, yes, again, so here we have the sine wave less than your triangular wave, and it will yeah, so it will produce a high up to this point, and then similarly low up to this point, and then high up to this point. So you can see that corresponding to the minimum points, the duty cycle is low, and corresponding to the maximum points, the duty cycle is high compared to this. So when you average this kind of signal effectively, so if you average this in points, so we're getting is kind of this waveform. Whoops. So you can reconstruct the waveform after this. So when you pass this kind of signal through something called a filter. So do you know about filter? So filter is basically just removing this oscillating components and giving us out the DC part, right? Yeah, rectifiers are different thing. So filters are different thing. Yes. Yeah, so it looks something like this, like this. So this is something we call as a low pass filter. Okay, like how can you realize it's a low pass filter? So in this is a series inductance. So if Laplace domain, yeah, obviously just leave it low, omega L, and 1 upon omega C. So if your frequency is high, then the resistance of this offer too. So you know that any signal can be broken down into a number of components. That's as we Fourier we see. So for high frequency components, this inductor will be having a very high impedance, and for low frequency components, it will be having a very low frequency component. So it will allow high pass, well, high will be blocked, and low will be passed, right? And whatever signals somewhat they cross somehow through. So this now this projector here. So this is grounded, and for high signals, the omega, the capacitive offers low inductance, low impedance, yeah, this is inductance. So for high frequency signals, this will allow this part to the ground, and for high frequency signal, low frequency signals, the impedance is high, so it will block them, and they don't have to just travel or go away. So this is effectively producing a low power signal. So whatever these fluctuating components, if you pass them through this filter, so this will be giving out your continuous calm, so that will be a sine wave, right? Okay, so is that part clear? No. Right, okay, awesome. Now, apart from just these were a very crude implementation of generation of waveforms. In real life, in real industry levels, we need very high precision. So how we can create very high precision waveforms through some sort of digital electronics. So they are very powerful. They can process the data very well. We can control each and parameter with a very high resolution. So through microcontrollers, we can generate very high accurate pulse width modulated signals. And how? We are just going to talk about that. So in a microcontroller, like you have seen your Arduino, your Raspberry Pi, each and every has something called a timer module. So it's it's capable of keeping count of time very accurately, and it contains a specific counter. So this basically just counts 0, 1, 2, 3 up to a certain level and then resets itself after it overflows up over its capacity, right? So this counter just counts up to this value, and then we have a compare value. So we can just define how many key up to this value you count and then set the pin. So if you let me just get back to the board. Yeah, so have your count like this. So 1, 2, 3, 4, like in time it will count like this. So up to something some max value, say some period of the counter, which is we define as that, right? So it will count with time. So it will make some sort of a waveform like this. So it all have these discrete values 1, 2, 3, 4, 5, 6, like up to the resolution of the counter. So if it's a 16-bit counter, then this value might be like 65,000 something, 2 to the power 16, right? So it will count up to that time, and then it will reset itself. Actually, it can do two things. It can either count down back from that point, or it can actually directly reset itself to 0, and then start counting again. So basically, producing a kind of a sawtooth wave. Now, with this, we have a value. So as I told, this is all discrete values. So we there's a term called compare value that we define. So we define a compare value, say for 65,000, if I had a 16-bit counter, if I define like 32,000, something like that. So this value will be having a 32,000 at this, and it effectively produces a constant wave. It will be staying constant in time, right? And then your microprocessor compares this value continuously with this one. So effectively, that we just how we look before the generation of this. So it's based on the configuration. Let's say if I said that if the compare value is higher than your period value, do the 0. So it will this time up to this time it will post 0. And then when the compare matches and it's greater, the counter value is greater than the compare value, then do me high. This. And then just when it falls back, so the counter value is again less than your compare value, it will go low. And just the process simply repeats. And now, like that, you can just keep the compare value constant, or you can this is just a software. This can be programmed with one line of software inputs. It's something called a register. So you might be familiar with term register. So it's just a register, and its value can be modified through code. So how we whenever do. So this value can even it's not necessary that then if the compare value at this time was this, so it should be the same at the next cycle. It can be varied. It can be like this according to my need. I can modify it as my need. So even you can then even if through you can generate even a sine wave by telling the compare value to be this at this discrete times. So and even you can just create a sinusoidal pulse width modulation. So this very accurate control. This is on a 16,000. Some have 32-bit counters, 64-bit counters. Because like the computation power has no limits in these days. Okay, right. So these can be very precisely controlled, each of part of this. So this is how the microprocessors do it, and you can absolutely control the amplitude and the C slope. So if this is a period value. If I decrease my period value, say I just this was something 65,000, I say the period to be 32,000. This is also that I can define. So it will count like this. This reset and this reset. So the amplitude of the signal can be also be varied. So if you will see that After compare signal, whatever the produces, so in this case it's more than that, so it can, like, hopefully you get the idea with that. It's gonna be a little messy and we are short on time. So this is how we can accurately create a control wave using microprocessor codes. Okay, so there's this part is specifically when the counter counts up and then counts down. So this is something we call the center line PWM, because in this waveform, in this part, the PWM wave is at the center of yours. So this is called a center aligned PWM, right? And the concept is exactly the same. As you can see, as we change the compare value, the part above it changes, and the pulse width modulation is happening like that. And similar with this, we have here edge aligned PWM signals. So that part, it just counts down, it resets itself, and you can just load the value directly. So I say that I wrote the period value and then it will count down to 0. Then I'll just reload it and it count down to 0. And then it will be having a triangle waveform like that from the counter, and the compare value as you can change, and it will be producing a variable cycle like this. So for details, you can obviously go through the slides, and also can ask any doubt if you have right now or on the group itself. So that will be all that we have for today. In the next class, we'll be covering with the applications of these waveforms, how we actually apply them to circuits, what kind of switches we use, and how do we integrate them in our current scenario systems. Okay, so you can contact us for any queries, and thank you for that attending the session.